Okay, so finishing our 3.2 notes. So we do have questions where the derivative doesn't exist. Now, doesn't exist, I think the better phrase here is actually where the derivative is not defined. And that is the phrase that is actually in the problem. And that phrase, not defined, is very similar to undefined, and that is what it's talking about. So the function cube root of x, and it's very particular to odd roots. So when we look at this graph, we see that we've got like upward sloping lines, and then eventually we have a vertical point, and then it goes from vertical to more upward sloping lines. So if we were actually to graph the derivative here, it'd like come along and shoot up to infinity, and then it would come from infinity and slow down some. I'm not sure exactly what number it would hover about because it's not flatlining, so it's not going to go to 0. Well, we could actually, it just does a weird infinite thing. So we're going to use the limit definition of the derivative to show what the derivative at 0 is of the function cube root of x. So this is going to look a little wonky because dealing with roots is one thing, dealing with cube roots gets a little weirder. So let me make sure I make a little room. Yeah. Okay. So let's write down our limit definition. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, since we're actually only focusing at 0, let's actually go ahead and put 0 in place of x, because that's actually going to make this calculation way, way nicer. Otherwise, it's a mess. So still our limit. So f of just h will be the cube root of h minus f of 0, the cube root of 0. That's just 0, and subtracting 0 does nothing. So we actually just have the cube root of h divided by h. Now, one of the rules that we're going to have to remember real quick in calculus is how to rewrite radicals into rational. So radicals, square rooty, cube rooty things, into little fractional powers. Computer. All right, so the cube root of h is the same as h to the 1/3 power. And then we already, minus 0 is gone. And then on the bottom, that's h to the 1st. So I want to write this or keep this so it has a positive fractions, but it does in a moment, like we have a thing on top, a thing on the bottom, they're the same bases with powers. We can subtract the powers. That's our rule for exponents here. So I have 1/3 minus 1 whole. So 1/3 minus 1, let's, spitball that off to the side. 1 whole I could multiply by 3/3. So that's 1/3 minus 3/3 is negative 2/3. So instead of writing this as h to the negative 2/3, though, I'm going to move that h to the denominator. Well, no, I'll write it just so we all remember our exponent rules and we've got a written example. So at the moment, that is h to the negative 2/3. That is the same as 1 over h to the positive 2/3. Now, when I try to substitute in 0 here, I get 1 over 0. Normally, when we substitute h in at the beginning, we actually end up with 0 over 0, which is what we call an indeterminate form because we don't know what's going on. One thing going to 0 and another thing going to 0, it just gives us a big mess. It masks what's actually happening. 1 over 0, though, is something definite. We can define this, well, we can define that it's undefined. So this is that infinite limit situation. The tangent line at that point when we look at the graph is a vertical line. The slope of a vertical line is undefined. So when I try to evaluate this limit, I get 1 over 0 to the 2/3. It's 1 over 0, which is undefined, but we also call this infinity in limit senses. And vertical lines, we say, have undefined slope, but when we're talking about all these limits at infinity, that 1 over 0 undefined state can also be thought of as infinite slope because the lines to either side are like a really huge positive infinity number or a really huge negative infinity number, depending on whether the line was an increasing or a decreasing line. But the point being that we are going to have functions that are continuous that may have the occasional point where the derivative is not defined, where the derivative is specifically a fixed number over 0. Usually we get 1 over 0, but sometimes it might be like 3 over 0 or -7 over 0. Still undefined, or this idea of infinite. But when we're looking at graphs, undefined points are where interesting things happen. So as we start exploring more with derivatives, we want to remember sometimes when the derivative equals 0, cool stuff happens, like the top of a peak, the bottom of a valley. But sometimes when an infinite slope happens, interesting things happen on the graph. All right. Now we also have situations like this, that corner point, like we saw with the absolute value at the end of class. The derivative did not exist. The function was continuous. It connects at the bottom of the v for absolute value, but the derivative did not exist because it sharply changed from -1 to a +1. Here we see the same thing. My derivative on the left side of this tipping point, cusp point, is a constant because that is a straight line. It has a constant number slope, some positive number. In fact, let's go ahead and calculate it. Looks like it's going through the point 0, 1. And then it looks like the next point is 3 higher. So it looks like the slope here is a rise of 3 over a run of 1. So if I'm going to sketch this graph, now forgive me because sketching on black is a little weird to me. And then we look at our cusp point. That cusp point is at 2. So let's go ahead and mark 2 on our graph. And it looks like all of the numbers before 2, everywhere to the left of 2, the entire graph is that diagonal line of slope 3. So that means everywhere, and let me actually pick a different color. Everywhere up until we get to x equals 2, the slope is 3. Now, since this is our graph of the derivative, it is literally equal to that constant number slope. On the other side, though, we have a curve. And in fact, it looks almost like the graph was flattening out there, and then everything's decreasing. So it looks like just to the right of 2, like it was maybe at 0, and then all the numbers start going down. So it looks like from the other side, we're near 0, and then probably a diagonal line of some sort, because that looks kind of like half a parabola. And we saw very early the derivative of a parabola was 2x, like the derivative of x squared is 2x. The derivative of a downward opening parabola, negative x squared, would be negative 2x. So on the right side here, it makes sense that it's a downward going line. And that's where all of those tangent lines are going to be decreasing slope. So we should be seeing negative numbers. But the derivative at that point, the left side and the right side derivatives are not agreeing on a number. So at that value, the derivative does not exist because they're not agreeing. Now, that's not to say every piecewise function is going to be disagreeing. We can actually craft piecewise functions that are continuous. We did that already. That was the question on the test, like make the points meet. But we also can craft piecewise functions so they're differentiable. So that way, like one part of the graph does a thing and it's coming in at a particular angle. And as long as our other graph matches the angle, even though the rest of the graph may curve, as long as at the point they are matching the same slope, then we call that continuous. Now, it's awkward to craft a function to do that, but it can be done. And that's actually what happens when like people manufacture like steel frames. They'll take a pipe and then they'll put a bend in it somewhere. They can make it an awkward bend and then the pipe is all ugly bent, or they can construct a gentle curve that's little tiny bends. And that's kind of the idea when we're trying to do this continuity meetup, is make sure that it's nice and smooth instead of a hard corner. So that's our idea here is I want to pick A and B values that make this continuous at x equals -6 and differentiable at x equals -6. Now we are deliberately using functions that we can actually shortcut the derivative on. So remember earlier, I was just saying we did the derivative of x squared earlier. We did the formula. It is 2x. And then the derivative of a line, ax plus b is just some slanted line. Derivative is the keyword for slope. So the slope of that slanted line is a. So we're going to have two pieces that we're going to play around with here. We need to determine the a and b values that make it continuous and make it differentiable. So continuity means the limit on the left and the right side are coming together. So the limit as x approaches, now our approach value here is -6. So the limit as x approaches -6 from the left of f of x needs to equal the limit as x approaches -6 from the right of f of x. Now our left and right sides are determined by our inequalities in our piecewise function. So our left side, where x is less than -6, that's going to be the function ax plus b. And let me rewrite the limit. Now, when we're evaluating limits, if we can just shove the number in, we shove the number in. So this is a times -6 plus b. So we have -6a plus b. Now on our other side, when x is bigger than -6, our function is x squared. But we still have the same limit. The limit as x approaches -6. And again, we can just shove the number in. So -6 squared is 36. So I have an equation here. -6a plus b equals 36. This is not enough to solve for values of a and b. I need another equation, a different equation from the one I have here, and then I can find the spot where the two equations meet. This does give me some idea of how a and b relate together, but not enough to pin down particular values for them. This is where our differentiable side is going to come into play. So differentiable means the derivative on either side has to be equal. So we need to talk about f prime of x on the left side, and we want this to equal f prime of x on the right side. So remember, the right side, that x squared side, we did the derivative of x squared earlier. It is 2x. On the left side, the derivative of a line is the slope of the line. So the derivative of the left side is just the slope, which is a. Now, the point in question is where I need these to meet up. So this is, we're looking at not just the derivative, but this is the derivative at x equals 6. So all of this is for when x equals -6. Sorry, I said 6, -6. So we're going to substitute that in. So I have a equals 2 times -6. Well, that means a is -12. Ooh, I'm halfway there. And now that I know a value for a, we're just going to bring it on over here. -6 times -12 plus b equals 36. So 6 times 12, 6 dozen. 60 plus 6 times 2 is 12 is 72. Again, because I do too much mental math, negative times negative is positive. So I have positive 72 plus b is equal to 36. And then I'm just going to minus the 72. And b equals -36. So my function now, if I want to define it, if I want to fill in my a and my a is -12 next to the x, and then it would be -36, and then it's still x squared, and our boundary point is that -6. So I would have a decreasing diagonal line actually, until we arrived at -6, and then it would go down at 0, it would form the vertex of the parabola, and then it would go up. So that is how we also handle the differentiability. Now, the next section, we're going to cover all the shortcut rules. So you won't have to do this like whole, how do we do the definition of a derivative to do the differentiability here? Like, we'll have the shortcut rules to help us work these problems. And then we just had our summary, everything we covered. All right.